Hey everyone, and welcome. Today we're going to break down a concept from mathematics that is, believe it or not, everywhere, from the code running on your phone to how we figure out probabilities. We're talking about set theory, which is really just a super powerful way of grouping things together.
So here's our game plan for this explainer. First up, we'll get right to the heart of it. What even is a set? Then, we'll learn the special language used to talk about them. After that, we'll meet all the different members of the set family. And finally, we'll see how one set can actually live inside another one.
All right, let's dive right into our first and maybe most important question. What exactly is a set? We're starting from the ground up here.
And let's start by meeting the man himself, George Cantor. He was a German mathematician who, way back in the 19th century, pretty much invented this whole field. He's the mind behind everything we're about to explore. I love this quote from G.H. Hardy. It just perfectly captures how math is this timeless thing that's always evolving, but always fundamental. In set theory, it's a perfect example of that.
So, here's the official definition. A set is a well-defined collection of objects. Now, what on earth does well-defined actually mean? Well, think of it like this. You're throwing a party, and you've got a super strict VIP guest list. There is absolutely no confusion about who's on the list and who's not. That's a set. It's a collection where you can say with 100% certainty whether something belongs or not.
And this slide really breaks it down. Look at the left side, under well-defined. The vowels in the English alphabet? Yep, that's a set. A, E, I, O, U. No debate there. The rivers of India? We can list those. But now look at the right. The 5 most renowned mathematicians? Renowned according to who? Your list might be different from mine. Or the best cricket teams. Again, that's just an opinion. The second you introduce confusion or opinion, it's no longer well-defined, which means it's not a set.
Okay, so now that we've got a handle on what a set is, the next logical question is, how do we actually write one down? Well, mathematicians have 2 main ways of doing this, so let's check them out. And those 2 methods are called roster form and set builder form. You can kind of think of them as the grammar of set theory. With one, you just make a list. With the other, you write down a rule. Roster form is the most straightforward way. You literally just list every single member or element of the set. You separate them with commas, and you wrap the whole thing in these curly braces. Now, there are 2 really important rules here. First, the order you list them in doesn't matter at all. The set 2, 4, 6 is the exact same as 6, 4, 2. And second, you never repeat elements. For example, if you wanted the set of letters in the word school, it would be S-C-H-O-L. Even though there are 2 O's in the word, you only write it once in the set.
And here's a super simple example we've already talked about. The set of vowels in the English alphabet, written in roster form, is just V equals A-E-I-O-U. Easy, right?
Okay, on to our second method, set builder form. This one's a little different. Instead of listing everything, we just state the rule or the property that every element in the set has in common. The format looks a bit mathy, but it's simple. You read this as the set of all x such that x has property p. So let's grab our good old set of vowels one more time. Instead of listing them out, we can use the set builder form. We'd write it like this. V is the set of all y such that y is a vowel in the English alphabet. See that? It's the exact same set, just described in a completely different way.
All right, now that we know the basics, let's step into the zoo of set theory. We're about to meet a few special kinds of sets, and each one has its own unique personality.
So let me ask you a question. What if you tried to make a collection, but it turns out there's nothing that fits the criteria? Like you throw a party, but literally nobody shows up. Is that still a collection? Is it still a set?
Yes, it absolutely is, and it has a special name. The empty set, or sometimes the null set, is just a set with 0 elements inside. We use this Greek letter phi, or just a pair of empty curly braces to show it. A great example is the set of even prime numbers greater than 2. Well, the only even prime number is 2, so there are no numbers that fit that description. That makes it an empty set.
Next up, let's talk about finite and infinite sets. This is pretty intuitive. A finite set is one where you could, if you wanted to, count all the elements. Like the set of days in a week. There are 7 of them. It ends. An infinite set, on the other hand, just keeps going forever. Think about all the points on a line, or the set of all counting numbers, 1, 2, 3, and so on. You can't ever reach the end. That's an infinite set. Now what about equal sets? This one is exactly what it sounds like. 2 sets, let's call them A and B, are equal if and only if they contain the exact same elements.
not similar elements, the exact same ones. And remember our rule, the order they're listed in doesn't matter and repeats don't count. All that matters is what's inside.
This is a fantastic example to drive the point home. Let's say we have set X, which is all the unique letters in the word alloy, and we have set B, the unique letters in loyal. If we write them out in roster form, we get A, L, O, Y for X, and L, O, Y, A for B. Since the order doesn't matter, they have the exact same elements. So yes, set X is equal to set B.
All right, for our last section, let's put it all together. We've been looking at sets by themselves, but now let's explore the really interesting part, how sets can relate to each other.
This leads us to the idea of a subset. It's simple, really. A set A is a subset of another set B if every single element in A can also be found in B. We use this little symbol here to show it. Think of it like this. Set B is a huge concert. Set A is the group of people who have backstage passes. To have a backstage pass, you had to have a ticket to the main concert first, right? So the set of people backstage is a subset of the set of all concertgoers.
Let's look at a quick number example. Say set B is all the numbers from 1 to 6, and set A is just the even numbers from that group, 2, 4, 6. Since every element in A, the 2, the 4, and the 6, is also found inside set B, we can say that A is a subset of B.
Okay, now there are two final crucial rules about subsets that you just have to remember. First, every single set is a subset of itself. That kind of makes sense, right? And second, the empty set is a subset of every set. That one might feel a little weird, but it's a fundamental rule of the game in set theory.
So, to wrap this all up, let's end with a question for you. Right this moment, you are an element in the set of people watching this. But take a second and think about it. What other sets are you a part of today? Maybe the set of people who live in your town, the set of coffee drinkers, the set of music fans. Once you start looking, you realize sets are absolutely everywhere. Thanks so much for watching.